Hi, everyone. Welcome to today's webinar, Back to the Basics, Measurement Conditions. Presenting today is Hagen Hurlitz, Application Support Manager for Print and Packaging at X-Rite. I'm Robert Grotans, the Global Digital Learning Manager, and I'll be moderating today's webinar. I just want to go over a few things before we get started. Due to the number of people that are attending today's webinar, we will keep everyone muted. If you have any questions during this presentation, please feel free to use the questions function. And at the end of Hagen's presentation, we will have a few minutes to take some of your questions. This webinar will also be recorded, and we will follow up with an email at the end of this webinar so that you can view the recording again. So with that, I will turn it over to Hagen to kick things off.
All right, thank you very much, Robert. So yeah, welcome to our little webinar, which is called Back to Basic Measurement Conditions. So what I want to talk about today is basically, like the title suggests, really taking a step backwards and talk about the terms which are broadly used in color management and try to figure out what exactly is hidden behind those terms and how we can use different technologies and those terms to make our life easier when it comes down to colors. So before we begin, let's take one step back and talk about what actually is a color. Because before we start talking about different conditions and different measurement methods, let's briefly summarize what a color actually is. So a color is basically a system with three variables. So to see a color, we need to have different things in place. For example, what we need to have to see a color in printed packaging, we need to have light. So if we don't have any light, we can't obviously don't see a color. The next thing we need to have an object. So we need to have something to look at, of course, to get the color, right? And reflection in this example. And the last thing we need is an observer. So in this presentation, the observer is you, the viewer. So it could also be a measurement instrument, for example, which can be an observer. So somebody who's taking up the reflections of the object. Now, the tricky thing is here, when we talk about color management, we need to make sure that the light and the observer is always speaking a constant language, so that the terms are right and the conditions are right. The object, for example, print and packaging, could be a printed sheet. So when we talk about light, we need to make one thing clear. A light source is not equal to a lighting condition. To give you an example. The most common known light source we have in our world is obviously the sun. Now the question is the sun always looking the same? When the sun is rising, it's very reddish, very warm. It moves across the horizon, and in the afternoon, it's getting colder and colder till it finally sets and the light is changing again. So when we talk to get a lighting condition stable, we need to make sure that we're really talking about the right thing. So just talking about light source, for example, let's have a look at it under the sun, step outside. That's not a good description which light is used to look at an object. Now, how could this affect us, basically? So what we have the option to go with the ISO standard, basically, which defines D50 and D65, which sounds odd at first, but the D is short for daylight and 50 for 5000 Kelvin, or D65, daylight, 6500 Kelvin. So now you see this lovely little painting over here. And right now we are looking at it under a lighting condition of D65. So that's basically the standard which is used, for example, in textile or plastics. Print and packaging, we are commonly using a D50. Now, I changed the light, and you may have noticed or not noticed that the object, the picture, is slightly changing in its appearance. Because the difference here is that D65 is a colder light. So the higher the number, the colder the lightning giving your object its color. We can also go with lightning source A, which, for example, is the tungsten bolt, which was used at home. And as you can see now, the color is changing dramatically on our little painting over here, and it's getting warmer and the bluish is turning reddish. On the other hand, if we go with the D70500, the picture is much, much colder. The appearance is much colder. So we need to make sure when we want to evaluate visually an object, the color, that we always using the same lighting condition. Otherwise, we can have dramatic shifts in the appearance of an object. Another thing to note here is it's not only one light source usually you're looking at. Normally, it's a mixture of different lighting conditions you're looking at. So that's the recommendation, to use a light booth, basically, that you can get rid of all the surrounding lights and ambient lights. Because, you know, when I turn off the ambient light over here, you see the object is changing again. So once again, my recommendation, if you want to go with a visual assessment of things, please make sure to go with a light booth at least. Another point which you could raise or which you could make is, well, that's all good, fine enough, but maybe I just go to the supermarket, buy me a lots of different light bulbs, and then I put it in my place, and then I'm good to go because they should be the same. The reason why the ISO is, for example, printed packaging is clearly stating D50 is that there is something which is called metamerism. So metamerism is a phenomenon where you have two objects, which you can see here now. Those two objects under D50 look exactly the same. So you produce those two little pieces over here, and then you send one over to the customer, and let's pretend the customer is using a different light source. So you can see now one object is looking different under D65, and that's basically the challenge with metamerism. So metamerism means that you have a color, an appearance, which is looking exactly the same under lighting condition A, but different under lighting condition B. There are some tricks to get this effect controlled in a controlled environment. So, but another recommendation would be, if you really want to look at things and the customer as well, make sure that the customer is also looking under D50 to avoid unpleasant surprises. Okay, let's go back to our little painting over here. Now, we talked about the daylight D50 or D65. Often when you look at those conditions, there is a slash and there is a 2 degree and 10 degree right behind. So what's actually behind that? This is the observer. Now, what does it mean? What is an observer angle, which is always displayed behind those D50 or D75, for example? The observer angle is telling you what the area of view you're currently using to look at a picture. Sounds odd. What's the reason behind that? Well, this is coming strictly from our humans' biology and how our eyes are built and working. We have something which is called the yellow spot or fovea. It's a little area in the back of our eyes which have all the cones and the others, which now is missing the word, but where all those little things are centered to gather all the information you need to perceive a color or an appearance. Now, and to be honest, this is a really, really small place. So we humans are really just can perceive our environment with a tiny, tiny percentage of our human eyes. The rest is basically just doing our brain on the fly to give us all the information we need. So right now there is, we're talking about the yellow spot is between 1 degree or 1.5 degrees. So when you look at this complete picture on your screen, this little spot here is what you actually can perceive sharp. The rest is going to be done by your brain. So that means it's not possible for us to just look at the color separated if the color is nested around other colors. So if, like in this painting, if you have a wild mixture of different colors, it's not possible for your brain to separate those different colors. You will always get those other colors mixed in as well. For print and packaging, the ISO norm settled upon a 2 degree, which is, to give you an idea, when you stretch your arm to the full extent, you put up your thumb and you look at your thumbnail, that's 2 degree. So that is the viewing area which we are talking about when we are in print and packaging. And 10 degree, that's this area. That's basically when you once again stretch your arm and you look at the back of your fist, that's the 10 degree. So like I said, print and packaging 2 degrees, industrial applications, we're talking about 10 degrees basically. Why is that important? Well, if you look now at this picture and you try to count the black dots, you will see that you are not quite able to do so, because when you try to catch a black dot with your eyes, it's always disappearing. That's the observer, the 1 degree observer. You have only a small fragment you're seeing really sharp and focused with your eye. The rest is your brain looking for patterns, and those patterns are recreated inside of your brain. Now, every magician in the world is working due to this biology of our eyes. So if we have like an observer angle of 100%, no magician would have a show to set up. It wouldn't work because we could see what's actually going on. And that's also the reason why you sometimes are basically fooled by your eyes. All right, quickly summarize. So just naming a light source is not sufficient enough to talk about a different light. We need also to talk about the lighting condition. The observer degree is the area of view you're looking at something. So 1 degree, 2 degree, or 10 degree. The viewing conditions are defined in the ISO 3060-66-4. So if you're interested to read through the ISO, this is the one which is clearly stating how to use this. And the standard for the graphic industry, print and packaging, for example, is defined as a D50 2 degree. If you are in a different environment, this may be different. All right, now chapter 4. So let's talk about what exactly is a measurement geometry. So we talked about a lightning, we talked about an observer, but sometimes you stumble across different terms as well. And those maybe refer back to the measurement geometry. So why is that important? Well, the human perception is quite complicated. So as you can see, we have an object here, which is, well, it's a color. It's plain, it doesn't have any effects, it's not glossy, it's not shining, it doesn't have a rough surface, it's really just the sensation of the color which is hitting our eye. Now we have object B, which is an appearance. You see it has a structure, it has a surface, it has a certain gloss to it, and depending on the angle the object is right now, you see the appearance is shifting. So when we try to describe this appearance, it would be much more complicated because we need to take different physical things into the calculation. To give you an example, now, how does the measurement devices are doing the trick here? Because usually, once again, just the basics here, print and packaging, we differ between a 45 and 0 degree or 0 degree 45, depending, and a D8. So what's the difference? The 45-0 is basically created to measure a color. So it has a 45-degree angle, and this angle is not by chance. It's done this way so that you have the least gloss and reflection. When you read a paper, for example, or a book, you don't hold the book in a 90 or 0 degree angle. You always do the 45 degree by yourself, unconsciously, because that's the most pleasant way to read a book. It's the easiest way to get an information. So if we want to give a color, this instrument is exactly built this way. Now, if we want to get an appearance, you see it's much more complicated. So to give you an idea what to do here, so 45 degree is basically doing this, right? You have a hard angle and you get a reflection. And you see on the left-hand side, the color It's not that complicated. So we had a pretty even appearance, and we can measure it pretty easily. Now, on the other hand, the appearance, you see, it's not that easy to pinpoint which color the object has. Now, what is a D8 doing? A D8, or a sphere instrument, is working with a diffuse light source. So no directional light coming in and coming out. It's like scattering the light till it's broken in completely tiny pieces. And then you have like a light fog. And this fog is used to measure the color. You see, it's suppressing the gloss, and it's much more easier to measure actually an appearance. So we need to differ basically when we want to measure something. Do we want to measure a color, or do we want to control an appearance? To give you some examples, you see here we have a little gallery which has different measurement conditions. Now, what's the difference here? We see M0, M1, M2, and M3. Those are the measurement conditions for a 45 0-degree instrument. SCI, specular included, SCE, specular excluded, that's for a diffuse measurement condition, so for a sphere instrument. So now let's look at different samples a customer may have and look how those instruments are perceiving those samples. So let's have a look at this one. So just a color, maybe a box. It has no OBA, no gloss, and no surface effects. So when we put our exact, for example, the exact 2 on this instrument, you see M1, M2, M0 doesn't make a lot of change. M3 is slightly darker because it has a polarization filter, so it's suppressing a specific amount of light. And the sphere is perceiving this color darker because the sphere instrument is looking through a light fog on this object. Now, what we could also have is something like this. So piece of paper, and we throw some UV light on top of it. And you can see now it's quite different. Does it make a huge difference which lighting condition we use? So let's start with the obvious one. As you can see, the SCI and the SCE, now this has this example, no UV light. So it doesn't really talking to the OBAs, it doesn't activate the OBAs. So we get a pretty dark impression of a white paper. M3, polarization filter, also with an UV cut, suppresses the light, and also everything below 400 nanometers, so no UV light at all. M2, UV cut as well, get a grayish paper. Now with M1 and M0, you have the UV amount in your measurement. Now, what's the difference between the M0 and the M1 in this example? The M1 is defined that every spectrophotometer which is using 45 degree has the same amount of UV light. So if you have a mixed environment with different spectrophotometers of different corporations, those should have the same amount of UV lights. So when you measure, you should get the same result. M0, this has no filter. So depending on which instrument from which deployer you use, you could have a slightly different amount of UV light and varying results, basically. That's the challenge. Now, talking from an X-ray point of view, it actually is the coincidence that the UV amount in the M0 is almost identical to M1. So we will not encounter a lot of shifts in an X-ray exact or exact 2 instrument when you measure M0 and M1. Okay, let's look at different use cases. Let's have a look at this one. So this, for example, could be a wet ink. So you're printing something and it's not dried out, so no UV, for example, and this is how the instrument is looking at this. Now, through the reflection of the object, a light is not completely reflected back to the observer and is, well, basically just missing. It's lost, a piece of light, through the direct reflection back. So you can see what it does. M0, M1, and 2, it's perceiving actually the color darker than the M3 because the M3 is suppressing the light, the gloss, and is giving you an idea how the color could look like when it's dried. So use case, you have a wet ink, you measure with M3, and after the color is dry, it should match up with the M0. So the color is dry, the gloss is vanishing slowly. Because in the end, if you are a printing company, the customer is looking at the product which is finished. So the customer is not really interested to see a half-produced product. He wants to see how is the product looking like when it's on the shelf. And the customer usually is looking at it in a dry, state. All right, so let's have a look at this beautiful gold over here. So how's my instrument looking at gold? You see, and this is a good use case for a sphere instrument. The direct, once again, the same issue with the gloss color. A direct light has an angle coming in and an angle coming out if it's a surface which is reflecting all the light. You see the observer at 0 degree can't pick up a color. So when you took a 45-degree instrument and you measure a gold, you get a very dark brownish thing. Now, on the other hand, if you go with an SCI, a sphere instrument, you see you get a idea of the right appearance. So in this case, if you want to go with metallized surfaces or pigments, you should go with a sphere instrument. And to make it even more complicated, now let's assume the customer is coming up with something like this. So this is now super complicated, right? We're not only talking about a color and a gloss, we're also talking about roughness. We're talking about different levels of light scattering, second, third degree. This is now getting super complicated. And as you can see, if we want to have something like this, could also be a texture, for example. Maybe there is a different measurement technology we could use to get all this appearance correctly grabbed over here. All right, so just to briefly summarize, the spectral measurements are also defined in an ISO, which you can look up and use, and the physical properties define which filter and geometry you should use, basically. For printed packaging, graphic industry, M0, basically what I said is the null filter, M1 with a specific UV content. Now, sometimes you can stumble across M1 part 1 or part 2. What's the difference? Well, an M1 part 1 is with a physical filter. So with the exact, for example, you have a little lever on the back side you can push, and then there's the physical filter above the aperture, measurement aperture, and you get a physical M1 reading. This is the recommendation if you go with fluorescent colors, for example. That's the best and road you can go to measure those colors. M1 part 2 is a software calculation for the M1. M2, UV cut, and M3, that's the polarization filter you can use to suppress gloss. All right, now let's talk about what actually is a delta E. Now, let's try to look at it from a different perspective to make it more clear, I think. Let's assume we have here in our little gallery, we have two objects, object 1 and an object B. Now, if we move those objects slightly on the x-axis in two different directions, then we have a gap between them. Now, let's move this object up in the y-axis, and now let's move it to the back. Now you can see we have two objects which are identical but are in a different location inside of our little 3D room here. So what we could also do, now we could say, well, what about if those two were colors? Then we can go back and say, well, color A has this distance in the x-axis, this distance in the y-axis, and this distance in the z-axis. So we have three axes, and the room inside here, that's our difference. So, and this is what we're doing with the delta E. So every color we describe, we can put in the CLAB 3D room. It's basically a 3D model with three axes, A and B, and the L axis, where you can place all the colors we can measure spectrally. And when we move those colors in this room, we can calculate what is actually the difference, the room between those two objects. Now, That sounds good so far, but there is something to keep in mind here as well. There are some different calculations we can use. The most commonly used is the delta E76, which you can see here. It's a not that super complicated calculation. And the other one, which is fairly used, that's the delta E2000. Now you can see the delta E2000 is slightly more complicated. So what's the reason actually? When the delta E LAB values have been created back in the days in the CLAB color gamut, the goal was to create a room which is close to the human perception. So when you move to colors in this room, the humans perceiving the colors should perceive it the same way like the colors are moving. Unfortunately, this goal wasn't quite achieved. It was a really good achievement, the LAB color gamut, but the colors were not mixing up with the human perception. So what we did then was not trying to correct the CLAB color gamut. We were correcting the equation how to get to an accurate result. So, and that's the delta E2000 basically. So the delta E2000 is correcting the color space CLAB. The question always is, well, which one to use? My recommendation is always to go with the delta E2000. But now let me quickly go to the summary. There are an ISO for the graphic industry, the 2013-2, which is defining AB or 76 for offset printing. The -7, which is for proofing, defines a delta E2000. It's pretty safe to assume that the delta E AB or 76 will be moved later on to 2000 for offset printing as well. Yeah, so what's to take in consideration here that the visual sensitivity with the 76 can differ by factor 10. So the factor 10 referring back to the human perception. Delta E2000 makes it more cleaner and slicker so that you have a better correlation between the human perception and the actually measured value you get from the instrument. So clear recommendation, I would only recommend to go with the delta E76 if you're planning to get a PSO certification. Otherwise, I would recommend you always go with the delta E2000. All right, we're slightly overdue, but thank you very much. And let's see if we have any questions.
Thank you, Hagen. We do have a few minutes for questions. If you do have a question, feel free to submit them now. While I give you additional time to submit questions, I am going to launch a polling question. If you are interested in reaching out to someone for more information or finding out about our products, feel free to answer this question, and let's see what questions have come in or if anything is coming in. Let's see here. We have a question about measuring metallics. Someone's asking if they can use the exact to measure metallic colors, or maybe you can recommend a better instrument to do that with.
Yeah, so I would not recommend to go with an exact because the reason it's a direct 45-degree measurement instrument. So think of it, the light coming in from an angle, and what we perceive as a gloss, so metallic is a gloss basically, is when the light, the energy is coming out on a specific angle again. So coming back to my example with the gold, if you measure a gold with an exact, the exact will tell you it's a dark brown. I would recommend to go with the sphere instrument with a CI62, for example.
Going off of that, which X-ray device allows SCI and SCE measurements?
That would be our CI6 series.
Is there a reason D50 is the standard for printing and D65 is the standard for photography?
Well, you know, those standards shifted historically often. So I can't give you a reason really why the ISO committee settled on D50. It is what it is right now.
If there's no OBAs in a substrate, does it make a difference if you use M0 or M1 to take a measurement?
No, you will get the same results.
Let's see, we have time for one more question. What's the best way to measure a varnished and unvarnished area of a print and get the same color without getting different readings?
Well, it kind of depends which varnish you're using. There are 100 different varnishes on the market. So if you're talking about a really high gloss varnish, it really comes down to the degree of the gloss, basically. So what I always recommend is, if you're not quite sure if you have how glossy your varnish is, just grab an exact, measure an unvarnished and varnished area, and check if you have a huge difference. Usually, if it's a semi-gloss, you won't have any trouble. If it's a really high gloss, maybe you should consider to change your workflow, how to measure there.
That was the last question we have time for today. So this will mark the end of our webinar. I see we have a lot more questions, so we will follow up with you if we didn't get to your question. Again, you will also receive a link to this recording in a day or two. So I'd like to say thank you everyone for joining and have a great rest of your day.
Thank you very much.